Welcome to Week 6, Lecture 3, an example of ANOVA. So we have an independent measure design experiment that was designed to measure the effectiveness of 3 different types of pain reliever. We'll call it pain reliever A, B, and C. A fourth group received a placebo or a sugar pill that was also tested. The purpose of our analysis is to determine whether these sample data provide evidence of any significant difference among these 4 drugs. The dependent variable is the amount of time that a subject can withstand a painful hot stimulus. And here we have our data. So we have 4 different columns. We have a placebo, so this group didn't receive any drug, just a sugar pill. We have drug A, drug B, and drug C. And we want to know if any of those resulted in a significant difference in terms of how long an individual could tolerate the pain. Okay? So before we start, these are the values that we're going to need when we get to step 3 and we have to calculate our ANOVA. And so I'm just going to put them out here for you. And for your own benefit, I would strongly recommend that maybe you compute these values. You can feel free to use Excel to get the totals or the sums of squares if you prefer, but it's really helpful if you could fill in this table on your own because it'll help you understand the concepts behind ANOVA. And I don't expect you to do this necessarily for the homework assignment, but I just thought it would be helpful for you to do it here. On the next slide, I'm going to go ahead and present the answers. So if you haven't already stopped and tried to compute it on your own, please do so now. So these are the values that I obtained. And you can feel free to pause the presentation right here and copy down the values and make sure you got all the values to match up to the values that I have here. If for some reason your values don't match up and you're not sure why or how I got those values, this is the key that just goes and shows how I added things up. So you'll have the label, the formula that I used, the values that I plugged in, and the answer that I obtained. And that goes for all of these. So you can have that for yourself. If you have not worked it out, you might want to double check and look at this stuff. It's really not that far from what we've done this whole time, but because we've had so many groups, we're doing what we did with one group now 4 times. So it's tedious and long, but it's practicing it will really help you kind of get the idea of what's going on. Okay, so now that we've gotten to this point, let's go ahead and go on to hypothesis testing. Step 1 of hypothesis testing is, as always, the first step is to state the hypotheses. So let's go ahead and do that. We'll start with the null. And again, remember the null usually states that there's no difference. And so what we would say is that our group, so the mean of the population of the placebo group is equal to the mean of the population of drug A is equal to the mean of drug B and equal to the mean of drug C. So in other words, there is no treatment effect. Next, we need to talk about the alternative. The alternative hypothesis states that there is a difference. In other words, at least one of the treatment means is different. And the reason we do this is because in general, you have a multitude of different possibilities that you can get where the treatment has no effect. For example, you can have you could have a situation where the mean for each of the groups is different from one another. You can have an example where the mean for group A, B, and C is the same, but the mean for the placebo is different. You can have an example where the mean for the placebo and drug A is the same, and the mean for drug B and drug C is the same, but those means are not equal, and so on and so forth. So here's some different examples of possible combinations. So rather than list all possible combinations in general, it's just common to state that at least one of the treatment means is different. So if you feel like listing all possible combinations, by all means, feel free to do so. However, it's not necessary. You can simply state that at least one of the treatment means is different. Now we can go on to step 2 and set our criteria. So let's go ahead and select our alpha level. I'm going to go ahead and pick an alpha level that we've been using this whole time just to stay somewhat consistent. So we'll set our alpha level of 0.05, but again, you can set it to 0.01 or 0.001, and oftentimes it'll be something that's given to you in a word problem. But for this example, we'll go ahead and set it at 0.05. And now we just go ahead and need to calculate our degrees of freedom. So our degrees of freedom total is just capital N minus 1. And if you flip back to our first table that has all the values, we'll see that N is equal to 20. So degrees of freedom is simply 20 minus 1. Our degrees of freedom between treatments is the number of treatments we have subtracted by 1. We have 4 treatments. We subtract 1 and get a total of 3. Our degrees of freedom within is capital N subtracted by K. So that is the total number of subjects that we have in the experiment, subtracted by the number of treatment conditions that we have. So that would be 20 minus 4, and we get a value of 16. So now we can go ahead and grab the source table. So we can go ahead and bring up our source table, and remember, I strongly recommend if you're computing any values by hand for the ANOVA that you use a source table. It'll help you keep track of all the information that you're computing, as well as help you double check your values. So now let's go ahead and input all our values for our degrees of freedom between, within, and total. And now that we have these values here, we can always double check and see if our math has been correct. So the between plus the within treatment value should always equal the total. So 3 plus 16 is 19. So far, so good. Now let's go on to getting our critical F value. And I just want to stop and say, our text obviously does not go into detail about ANOVA, although it is an important statistic to use, and it doesn't have and as such, it doesn't have a table. So to get an F table, you can either just look one up online, or don't worry about it. You shouldn't be computing these by hand anyway. Feel free to use Excel, and Excel will give you those values for yourself. It will give you the p-value, will let you know if you're correct or not. So in this step, if you don't have a table, I would accept you just presenting your degrees of freedom and stating, I don't have a copy of the F table, so I'm going to use the p-value from Excel, and that is more than good enough to get full credit for this section. I'm sorry about the fact that you don't have the table, and that's why it's it's good to look up, but it's not pertinent. I would expect in the future, if you're ever running an ANOVA, you're going to do it using a software and not by hand, especially if you have a large data set. So enough about that. Let's go on to the next step. Step 3, compute our sample statistic. So we can go ahead and compute the different values for the variance first. So we start out by getting our total sums of squares. And the sums of squares total is equal to the sum of all the x values squared subtracted by g squared over n. And if you come over here, we have the sum of x squared already computed, we have our g already computed, and we have our n computed. So all those values are in our data table that we did at the beginning of this example. And so there they are in red. And so now I've taken those values and plugged them into the formula and went ahead and solved. And I got a 82 for my sums of squares total. And hopefully you got the same value. So let's go ahead and place that value into the source table. And now let's go ahead and compute our next sums of squares. Next, we're going to compute the within treatments sums of squares. So SS within treatments is equal to the sums of squares inside each treatment. So in other words, the sums of squares for each of the different groups that we have. And we have 4 groups, and we have already computed our sums of squares down here. And here it is in red. So we just take these four values and go ahead and add them. And we get a value of 32 for our sums of squares within treatment. And now we can take that value of 32 and place it in the source table. At this point, you can eyeball and know what the sums of squares between treatments is just by looking at this, because 82 minus 32 should give us a value of about 50. You can go ahead and plug in 50 and solve for your F ratio at this point if you'd like. If you're not comfortable with the math and you like to double check your answers, please feel free to do your sums of squares between treatments, which is what I'm going to do next. So our between treatment sums of squares is noted by sums of squares value between treatments. It is equal to the sum of the total of each group divided by n, all subtracted from g squared over n. So let's go to our table. So we need the totals for each of the group, n for each of the group, and then at the end we subtract that by g squared divided by n. So we're going to go ahead and place those values here, and you could even actually possibly place a parentheses over here, because remember when we talked about order of operations, the please excuse my dear Aunt Sally, the summation means that we add those t first, and then we subtract this n part of the equation. Okay, and so if we take the total of each group subtracted by n and add all those values together, we get 230, and then we subtract that from 180, and we get a value for the sums of squares between treatments of 50, which is what we expect. So we can go ahead and place it in the first table. And if we hadn't done the math backwards at this point, we could go ahead and just add 32 plus 50 to get a value of 82. And now we know that we have done all our math correctly. So next is to get our mean squared values. So, of course, the formula of double checking. So now let's go ahead and get our mean squares between treatments, which is simply the sums of squares between treatments divided by the degrees of freedom between treatments. And so those are the values that we have here. So we can go and take 50 and divide it by 3. And so there we have 50 divided by 3 equals 16.67. And we can go ahead and place that number in the table. Now, on to computing our mean squared within treatments. And our mean squared within treatments is simply the sums of squares within treatments divided by the degrees of freedom within treatments. And here's our summary table. And here's our values, 32 and 16. So we simply divide 32 by 16. And 32 divided by 16 gives us a value of 2 for the mean square. So we go ahead and place that in. And at this point, there's no more checking our math. So hopefully we've done everything correct. And now we simply solve for f by taking the mean square between treatments, which is the difference that we expect to get between our treatments plus error, and we divide it by the mean squared within treatments, which is just our error. And what happens is we take the following values of 16.67 and we divide it by 2. So 16.67 divided by 2 gives us an F ratio of 8.33. And if you think back to last lecture, that's a pretty large F ratio. So it's a pretty good guess that we ended up rejecting our null. But let's go ahead and place this value in the source table, and then go ahead and find our critical F from our previous step 2, which I talked about, but I don't remember if I actually verbally said what the critical F value is. Let me just flip back in my notes. I'm sorry. I think the critical value is 3.24. So it looks like we are pretty comfortable in saying that this is a significant test, but let's go ahead and go on to step 4 and do it correctly. Okay, so we have an F obtained of 8.33, and our critical value is 3.24. And so if we can either compare them by saying that F obtained is greater than the critical t-value, or we can graph it by placing the F obtained on the graph and seeing that it is in the shaded or in the critical area, which means that our F obtained is in the critical region, so we reject the null, and we can conclude that there are significant differences among the treatments. In other words, not all the treatments are the same. However, we actually do not know which treatments are different. So in other words, we have not determined which ones are significant from the other ones. So if you think back to our step one where we stated our hypotheses and we had a variety of different possibilities that could be possible for our alternative, we just said that at least one difference exists. So at this point, if you wanted to know which difference or where that difference existed, what you would need to do is run post hoc tests. Now, I'm not going to go into detail on post hoc tests, but simply what post hoc tests are comparisons done after the ANOVA that allow you to determine where those differences are. And there's a lot more behind this than what I'm stating here, but I just feel like I don't want to make this any more complicated than it already is. So it's enough for you to simply know that there are post hoc tests out there, and you do not need to know how to do them. Now, let's go ahead and try to do this example using Excel. So here's an example of the Excel spreadsheet, and I've placed in here the different treatment conditions that we have, and I've labeled them. And so you can do this one of two ways. You can go to data analysis, and then you get the following pop-up window, and you just scroll down until you find ANOVA. It's actually up here at the top. We're doing a single factor ANOVA. There are two factors, and two factors with or without replication. I think that has to do with the dependent and independent types of ANOVA, but we haven't actually really gone over those in the class. We just kind of alluded to them a little bit in one of the lectures. So the only ANOVA that we are going to cover is the single factor ANOVA. And go ahead and click on the OK button. And when you click on the OK button, you need to go ahead and put in the input range here, so where your values are, and I inputted the values. Now keep in mind that if you are, like in the example that I have here, the labels are listed here. So if you include A1 through 6, you need to click this little button here that says labels are in the first row. Now I put A2 through A6, so I don't need to click on that button. Just be careful and conscientious of this. Mistakes can be made if you are including the labels as data values. And then we signify how the groups are, how they're grouped. And in this example, each column represents a different treatment. So we click the column button. If we had listed this in a different way, we might have been able to click the row buttons. But the way it's presented here, the column is the grouping variable, or the column is what the columns distinguish between the different treatments. As you can see right here. And now we just go ahead and click the OK button. And now we get this beautiful result here. And let me just make it a little bigger for us. And so if you look here, we get the mean for all the groups. But what's really interesting is down here is, what is it? It's the source table. It's the same table that we have been using this whole time. And if you look here, our values for the between group sums of squares and the within group and the total all match up with the values. What we have here at the end of the table are two things that are not in our source table, but are very helpful for you. Here is our F critical. So Excel gives you that value. So if you didn't have a table, which you don't unless you looked it up online, you can get your F critical from right here. Also, if you'd rather not use the F critical to make your decision, you can use your p-value to make your decision. So in other words, you would say your p is less than 0.005, or sorry, 0.05. I mean, technically it's less than 0.01, but anyway, 0.05 was the value that we established. So there you go. Pretty easy, a lot easier than to do it by hand, of course, but it never hurts to make that practice just so that you learn in the future when you do your own research. I'm sure that you will be using Excel or some other statistical software, and you will not be doing it by hand, so it's always good to know how to do these things both ways. Oops. Here's my sorry, I got ahead of myself a little bit there. I think it's late and I just want to be done, and I'm sure you do too. So here's our F value, and it matches up with the F value we computed. And then again, like I said, our critical and our value. And so here's our source table from before. I just wanted to bring it back up just in case you guys didn't have it written down, although I'm sure you do because you're listening to the lectures, which makes me think that you um, are really invested in getting this information. So here you go. I guess that is it for this final lecture. I hope that you enjoyed this example of ANOVA and that it wasn't too difficult and hopefully made things a little clearer for you. Thank you so much for your time. You have a good weekend.